טוב, שלום לכולם. אנחנו היום מארחים את טל וגנר ממייקרוסופט ריסרצ'. טל עשה את התואר הראשון בטכניון, השני בוויצמן, השלישי ב-MIT. הוא יספר לנו היום על השוקי של דאטה ואלגוריתם.
כן, אוקיי, אז תודה רבה על ההזמנה. אני הולך להעביר את הטוק באנגלית כי ככה אני אגיד, אבל אם זה בסדר, אני הולך בסדר. Okay, so let me get started. I'm going to talk about the role of data in algorithm design. Let me just turn this on. Okay, cool. Okay, so I'm generally interested in connections between data science and algorithms. And this goes into directions. So the more obvious direction maybe is to, I can tackle my mask, right? By the way, I think it's. Okay, so I'm generally interested in these connections between data and algorithms, and this goes into directions. So one direction is maybe the more obvious one, to design algorithms that can handle better data or more data or larger data sets. And the other direction is maybe the less obvious one, which is the one I'm going to concentrate on in this talk. Which is to use data to design better algorithms. And let me start with how maybe the traditional view of computing is, how we traditionally design algorithms. So we first design the algorithm, then we apply to our input, and this is it. And this is simple, but this is maybe not quite how things look today anymore. So today, usually, before we ever get to designing our algorithm, we already have access to a large amount of data that we've collected and curated. And it's generally believed that this data encompasses opportunities for gains in performance or in accuracy. And then we design the algorithm with this data in mind, and then we can apply new inputs that come our way. So let me give you a couple of examples for algorithmic problems that we usually solve in this data-driven framework or with data in mind that I'm sure you all know. So one is a large case search. So we usually start by pre-processing our search data set. And this allows us to construct an index or retrieval index, which is a fast mechanism to quickly answer new queries. And then we can apply to new queries that come our way. And another example, of course, is machine learning, where we usually start by training on a large data set that we've collected. This gives us a trained model, and then we can apply this trained model to new inputs via inference. So this retrieval index and these trained models are two examples of algorithmic mechanisms that we usually design with data in mind or based on data. And the point is that you can potentially think about extending it and generalizing it, and maybe thinking about every problem and designing every algorithm in this data-driven way. So the opportunity here is for data-driven and learning-augmented algorithm design. Data-driven because we want to make use of all this data that we collect and incorporate it into the process of the algorithm design itself, ideally in an automated manner. And learning-augmented is because usually or many times it's not clear how to use this data. So what exactly are we going to do with this data that we have collected to improve the way we design algorithms? And this is just the kind of problems that machine learning tends to be very good at solving. So taking some past data or existing data and using it to say something meaningful or useful about new data that we haven't seen yet. One question you may ask is what is new about this? Why am I talking about this now? And why hasn't this been done maybe throughout the history of computing? So
אוקיי, יש מישהו שעוזר לי, אני חושב שזה רג'ה, תודה רג'ה.
אני אחתום על הדברים אחר כך, בסדר יאיר?
בסדר גמור.
אוקיי, אני פשוט חייב לפרוש.
רמי או מי שזה לא יהיה, תעשו מיוט.
גיא אבן, תשתיק את המיקרופון.
כן, גיא אבן. גיא אבן, תסגור את המיקרופון.
אפשר להשתיק אותו גם, אפשר להשתיק את כולם.
Okay, yeah, I'm sorry about that. So this was a short break. Why is this new? Why haven't we done it before maybe? So two things happened. I mean, to some extent this has happened before. So there are definitely papers from decades ago even that go along these lines. But recently this has become more prominent because we are in a point of time in computing where two things recently happened and then they make this more relevant. The first is that, of course, we are in the so-called age of big data. So every technological entity, every consumer of algorithms collects and curates this large amount of data and has access to at least a lot of data, and we want to somehow make use of that. And the other is, of course, dramatic advances in machine learning, especially deep learning and neural networks. So if maybe a few years ago, a decade ago, we didn't yet have the tools to make use of all this data that we collect to design better algorithms, then maybe now we already do. This is the overall view of the talk, what I'm going to talk about. My work on this topic spans three areas in large-scale algorithms. One is high-dimensional similarity search and metric data. The other is efficient algorithms for linear algebra. And the third is learning algorithms for data streams. In this talk, I'm going to only get to cover the first two of them. And I'm going to show you how we can use data and then how we can use machine learning to improve the way we design algorithms in these spaces. And I'm also going to make the point that these are not two separate areas and these are not three separate areas. Underlying all of them is the same set of techniques from the world of high-dimensional metric quantization, which turns out to be very useful for designing scalable algorithms in all of those spaces. Okay, let me start with high-dimensional similarity search. Let me know along the way if you have any questions, and I'm going to start by defining the problem. So the similarity search problem is very simple. We usually start with some raw data set, a data set of objects. They can be images, they can be text documents, they can be anything else. Usually, almost without exception, regardless of what the data modality was, we embed each object as a point in a high-dimensional space. So we take each vector, we represent it by a long list of numbers, which is called the feature vector, and these feature vectors can be viewed as points in a high-dimensional space. And now we have a natural way to measure similarities between those points. For example, the simple Euclidean distance in this space. So there are many ways to generate those features. Classically, there were handcrafted ways to design features for different data modalities. And more recently, it's more popular to do this automatically using neural networks. For our purposes, this is not going to matter. As far as we are concerned in this talk, the data starts as a set of points in a high-dimensional space, R to the D. And the similarity search problem is that we get a new object, we embed it into the same space, and the goal is to return the most similar points to it from our data set, which are defined as the one that minimize the Euclidean distance, for example, in this space. So this is the similarity search problem. Let me give you the overview of how we usually solve it in large scales. So the typical system has two stages. We start with our data set, billions of points in R2D. The first stage is partitioning. So we take the data set and we break it into a few pieces. And the second stage is compression. So we take each piece and we compress it to fit on the memory of a machine. And this collection of machines or network of machines is the search system. And then when we get a new query point, the idea is to identify a small number of the most promising pieces to search through, and then look for similar points in the compressed representations that we have stored on the respective machines. So this is how the system looks like. I'm going to talk about both of the stages. I'm going to start with the compression stage. So in metric compression, what is the task? I want to compress my data. So as what? What am I trying to preserve? What I want to preserve is the distances between the points, because this is what I need to know to perform similarity search. So more precisely, the problem is defined as follows. We have endpoints in R to the T. This is the input. We need to produce some representation of this data. And this can be any bit representation that we want, as long as it has the property that given any two indices of points or identifiers of points, we can you recover the distance between them up to a bounded relative error of at most epsilon. And our goal is to minimize the bit size of this compressed representation. This is the definition of the problem. Why is it important? So for large-scale search, we usually have to store the points on the main memory of the machine. So for example, Facebook Research have one of the industry standards today for large-scale similarity search. It's a library called FICE, and they claim outright that they only support the main memory because according to them, there's no point in supporting anything else. It's just too slow. Basically, the bottom line is that the less compression you have, the more machines you need in your system, and scaling up the number of machines is a major scalability bottleneck. This is basically where these systems get stuck. Yeah.
אבל הגישה שלך היא לשימור של המרחקים רק במובן שהאינפורמציה נמצאת שם איכשהו, או שגם אפשר למצוא את הקרובים מהר?
מעולה. אז כמו שאני מפרמל את זה פה, אני הולך לדבר רק על התכולה של האינפורמציה. זה כמובן חשוב, ואנחנו גם נדרוש שתהיה דרך יעילה גם לבצע את התפיסה וגם לבצע את הריקאברי, אבל זה...
כאילו הייתה להם דרך יעילה לבצע את הריקאברי, אבל אנחנו לא נמצא ל-SSD.
אם הייתה דרך... אז הבעיה פה היא לא כל כך לבצע את הריקאברי, כמו ללכת ל-SSD מלכתחילה. זה כבר בפני הסוף אני אוקיי. So I'm going to say a bit more about that later, but the difference is right for the recovery. Okay, so this is the definition of the problem. This is the metric compression problem, and how can we go about solving it? So there's very nice theory behind it, the classical theory of the Euclidean dimension reduction. So a very famous theorem by Johnson and Niederschauss tells us that we can always take the points, no matter what the original dimension was, we can always reduce it to only log n over epsilon squared, and still the distances are going to remain approximately the same. And this is a very strong statement. Just to make the point, if we wanted to represent exactly the distances between endpoints, we know that we might have needed as many as n-1 dimensions. This is not difficult to show. And this theorem tells you that if you are okay with approximation, with this small error, then you can improve the dimension up to exponential. So this is a strong statement, and it's also obviously a type of compression result, right? Because we take the representation of each point and we make it that much smaller. It doesn't quite tell you what is the bit size of this representation. You need another step for that. This also has been done in some classical works in similarity search. The one that there's a few of them. The one that does it in the most general way for our purposes is the one listed here, which is also from 98. This is called quantization. The bottom line, and I'm going to go into a bit more detail later, but the bottom line is that you can represent each point using only log squared n over epsilon squared bits, and the distances are going to remain approximately the same. So this is the compression rate that you can get with this technique, with data oblivious technique. And I'm also going to say exactly what I mean by data oblivious in a second. But just one last comment before that is that these theorems are also efficient algorithms. So basically everything here boils to a random projection. You take your point, you project them on a randomly selected lower dimensional space, and the distances with high probability are going to be approximately the same. So this is what we have in theory for data oblivious compression. But again, this is not quite how things look in practice. So this is a very practical problem. It is solved in practice often, and the most successful practical algorithms use a completely separate set of techniques. Yes.
You speak very fast and very low voice. I find it hard to follow.
Okay.
If you could help me a little.
Yes, I'm sorry about that. I am going to try to control the speed. Thank you also. The volume, I'm going to do my best, but this is a problem that I have less control over, but I'm going to do my best. Okay. Thanks. Okay, so the algorithms that are used in practice, they look very different. They use very sophisticated and very involved optimization techniques on the entire data set. So this is the distinction I want to draw here between data oblivious and data dependent. In data oblivious techniques, I take each point and represent it in a way which is intrinsic to that point. So it is independent of the other points on the data set or independent of the data set it is part of. Whereas in data-dependent compression, I'm going to represent each point in a way that can depend and will depend on the data set it is part of, or more precisely, it is going to be one big representation from the entire data set. And when I say this is the more common approach in practice, I mean two things. So first, there are the applied research communities in computer science. So for example, this problem comes up a lot in image retrieval. There's a lot of works on it. These are some classical references, and they use these type of techniques. And I also mean the larger scale similarity search systems that we have out there today. So all of them use this complicated and very computationally heavy optimization techniques. And the question is why? Why go through all this trouble? Does data dependence actually help here? And if so, then why doesn't the theory tell us that? So this is the gap that we wanted to close, and this is what we have done. So yes.
So the general approach on the left don't give the same result as the one on the right. This point.
Yeah, so this is what the theory tells us to do. This is the bound you get in theory, and this is what is going on in practice. And prior to our work, there was no analysis of why these techniques.
And it give way better results.
In practice, yes, yeah. These results they don't perform anywhere near as good in practice as those. Yes.
But this has the limitation that it's difficult to add points, right?
So even just without adding points, take a data set and represent it in a way that I can compress the distances. Even just for that.
No, I asked if you're using data dependent, then if you add new points,
this is a.
לא בהכרח, אם זה תלוי בהתפלגות, והנקודות באות מאותה התפלגות, אז אתה גם יכול להוסיף.
Yes.
So you have to look again.
Yes, so definitely this is a challenge. So data oblivious techniques have the advantage that it's easy to add new points. Here it's not as easy, and I'm also going to get there. I'm going to talk about it a bit later. So let me go through the main theoretical result, at least for this part of the talk, that we can actually get a better compression rate of only log n over epsilon squared per point. This is also tight. This is the first improvement over this classical quantized and natural reduction bound that we had for something like 30 years and was log squared and in bits per point. And importantly, you probably cannot get this result using data-dependent techniques or anything better than log squared n bits using data-oblivious implementation. You have to use data dependence, and this is also proven. Yes.
What should we think about epsilon compared to log n?
So for this purpose, think of n as going to infinity and epsilon as a very small constant.
No, so still constant.
Yeah.
So log n is much larger than 1.
I don't know if it's a good regime to keep in mind. Maybe epsilon can be smaller, but it can be not very small. In the extremely small regime, first it's not practical, and second it's a different world of techniques. Okay, so now let me just give you in 2 words maybe why data dependence matters here. So qualitatively, why do we get some improvement out of it? So in data oblivious compression, as I said, I try to represent each point in an intrinsic way that does not depend on the rest of the data set. In a sense, this means that I'm trying to approximate its absolute location in the space. Whereas in data dependent compression, I can maybe store the locations of the points relative to each other. So this is a very simple concept, and this is usually how we tell each other how to get places or where things are. So it may seem intuitive that we can get some advantage out of it, and this turns out to be the case. And I'm going to go into, again, a bit more details about the algorithm in a second. And just one more comment about it is that this is an asymptotic worst case improvement. So it's not like we improve for some data sets or for nice data sets or data sets that have some structure. The improvement is for any data set. And this means in a sense that every data set, at least for this problem, has some structure that you can potentially computationally exploit if you uncover it. And this is a phenomenon that manifests itself over and over in a few contexts in data dependence. We are also going to see it again in this talk. So this is something to take away from this theorem. So data dependence doesn't mean that you cannot improve in the worst case unless you sometime get new data. It means that there is a structure to the data set. It can just be different structures for a different data set. Okay, so now let me try to give you a bit of a flavor of how this algorithm works. So my goal in this slide is going to be to give you the minimal toy example where I can still show you why we get this advantage. And I'm going to do it with a stoic data set where I define it as follows. The points are ordered in a way that each one of them is at distance 1 to some direction from the previous point. So a bit more, let me draw this. So this is the first point. The second point is the distance 1 to some direction. The third point is distance 1, and so on and so on. So this is the toy data set. What would a data oblivious compression do here? So I'm going to describe a slightly newer version of this compression scheme by Nogalon and Boat-Klatak, but it gives the same bound. It's just more convenient to describe here. It is going to quantize the points. So what does it mean to quantize the points? It means that I take my data set, I impose a grid on the data set. It's a uniform grid, and I'm simply going to snap each point to a corner of the grid cell that contains it. Now I can use those corners as proxies for my points. If I want the distance between some pair of points, I can simply return the distance between the proxies. And if the grid is fine enough, then I get a good approximation of the distance. And then the question is, what is the compression rate? So the question is, how many corners are there that I might have to end up storing? The compression rate is log of that, right? Because I'm going to store the corners. And it's not difficult to count here that the number of corners is n to the d, because n is potentially the diameter of the data set and d is the dimensionality. This is simple to count. So the bottom line is that I get log the number of corners, or d times log n bits per point. By Johnson-Lindenstrauss, d is log n over epsilon squared, and this is why we get this log squared n bound. In data-dependent compression, in our algorithm, instead of quantizing the points, we are going to quantize the displacements or the differences between the points, or those arrows. So I'm going to do the same hypercube snapping. I'm going to impose hypercubes on these arrows instead of the points, snap each one of them to a corner of the grid cell or the hypercube that contains it. And then I can recover proxies for my points by following inductively those quantized arrows, right? So I take the first point, let's say it's the origin, it doesn't matter, yes.
So previously you had a multiplicative 1 plus minus epsilon. But here, if they snap to the same point, then it becomes 0.
This is okay. Yes. So this is true. I mean, the result by Algorithmic, it's actually an additive approximation. You can make this into a multiplicative approximation. I'm going to show you in the next slide how. But yeah, you have to work. There's actually a hidden parameter here, which is the aspect ratio, the ratio between the largest and the smallest distance, and you have to control that. Then yes, the grid has to be finer than the smallest distance. Okay, so right, so I can recover proxy small points if I follow those arrows. So I take the first point, I add the first arrow, it's quantized, so there's some error here. So I get an approximation of the second point instead of the actual second point. And I can do this again and so on, and I recover proxies for my points. And again, if I want the distance between some sum of points, I can return a distance between the proxies. And again, the question is, what is the compression rate? And the point is that just because the way I define this data set, then each error has length 1. So the number of corners I might have to snap it to is only constant to the d instead of n to the d. Even though there are endpoints, what do I need to store for every point? I need to store two things. First, who was the head of the arrow? Who is the previous point? That's log n bits. It's a point among endpoints. And what is the quantized displacement? So what is the arrow, the quantized arrow? And as we said, this is log of constant to the d, so this is d bits. And this is why we get d plus log n instead of d times log n, which is altogether log n instead of log squared n. So this is where these improvements come from on this example, just for demonstration. Let me maybe say just a few words. What is the question?
Yes, about the previous thing. Don't you accumulate errors when you sum all of the displacements?
Yeah, so this question comes up a lot. It's not difficult to show because it's kind of subtle, but let me get to the, yeah, so it's kind of subtle, but because you add the arrow to the previous quantized point, the previous proxy, and not the previous actual point, you don't accrue this approximation error per point, and it's really simple technically to show that you don't accumulate too much error. So the error doesn't blow up.
This is just because this is the multiplicative approximation, maybe that's the thing.
I think I'm not sure if it's going to work for additive approximation. So possibly, yeah. But it's the error doesn't accumulate. Okay, yeah, I need to think about if it also works for additive error, but for the multiplicative case, it definitely works. Okay, so
אפשר לשאול רגע דרך עוד שאלה בזום?
בטח, כן.
למה מובטח שיהיה מישהו במרחק אחד שאתה יכול ללכת אליו? אולי הם מפוזרים רחוק?
מצוין, אז ככה אני בניתי את הדאטה סט הצעצוע שלי, בדיוק כדי שאני לא אצטרך להתעסק עם זה, ובמקרה הכללי באמת אני חייב להתעסק עם זה. אבל במקרה הזה, בשקף הזה, זה פשוט תכונה של הדאטה סט.
אוקיי.
ועכשיו באמת אני אגיע let me get to the general case. So what is the difficulty between the general case and the example? So the main difficulty is exactly what was just asked, that the leaps between the points, the distances between the points, they don't have to be of the same size. They don't have to be of size 1. They can be of completely different scales. And I have to somehow deal with all of these scales at once. Another difficulty is to define the ordering of the points, because general datasets don't have this inductive ordering naturally, but that turns out to be an easier problem. That's not difficult to get around. This scales issue is the main difficulty. And the way data oblivious compression handles it is simply, this also answers your question, to do it once per scale. So the very simple solution of doing what we just described once for each scale. And this is why we get again this d times log n, because this is the number of corners per scale, and log n is the number of scales. And what we are going to do instead is use hierarchical clustering of the space to glue those different leaps of different scales together into something that still looks like a hypercube. So it's not exactly a hypercube, it's something that looks sufficiently close to being a hypercube with side length, which is not constant, it's not some constant scale, but it depends on the distances that I'm actually trying to approximate. So in this sense, this is a data-dependent hypercube, or at least its scale is data-dependent. And then we can snap those arrows pretty much like before, not just to the corners, but to some set of points inside, which corners and a little bit more, and get the same result. So this is roughly how we handle the scale, by gluing them together. This is the difficult part, into a sort of a hypercube. And this is, I think, all I can say about this algorithm in this slide.
אפשר רק לשאול שאלה עם עוד אחת? בשיטה הזאת אתה גם צריך אבל עדיין לוג לוג n בשביל הסקייל. זאת אומרת, זה לא לוג, יש לזה לוג לוג n הפסד.
אוקיי, מצוין. אז תנו לי להיות טיפה יותר מדויק פה. אז so for this slide I made a simplifying assumption that I didn't maybe make very explicit, there's actually another parameter here, which is the aspect ratio that I mentioned before, the number of scales. So I have the number of points, the approximation I want, and the number of scales. I assume that the number of scales is log n just for simplicity. The full bounds, so let me state them because this was correct. Data oblivious compression gives you log n times log phi. So log number of points times log aspect ratio over epsilon squared. And our result is log n over epsilon squared plus log phi. So this is exactly the log factor that you've spoken about, and you're correct. But because it is additive, then in the typical setting where the aspect ratio is polynomial and the number of scales is log n, then the total bound is log n. Okay. Okay. So yeah, there is some another hidden parameter here. I'm sort of suppressing it to give the typical scale of the result. Okay. So this is what I wanted to say about the algorithm. Now I want to move on to the
אבל אם אפסילון קטן, אז הקבוע של מספר הסקייל, הוא גם יהיה ענק.
אם אפסילון קטן זה קבוע.
הסקייל, עוד פעם, בדוגמה שלך זה היה נראה כמו פקטור 2, אבל אם אפסילון שלך הוא לא חצי, אלא הוא אלפית, אז עכשיו יהיה לך המון סקייל, כי הגרדואשן יהיו יותר קטנים, לא?
אז לא, כשאני מתכוון למספר הסקייל, אז אני סופר אותם בבסיס 2, אני לא סופר אותם בבסיס אפסילון. זו הפרמטריזציה, זה כמובן תלוי איך עושים את הפרמטריזציה, אבל זו הפרמטריזציה הסטנדרטית, אלא כמו שדברים שאמרתי הם תחת בסיס 2. אוקיי. So any more questions about the algorithm description or the result for compression? Okay, so now I want to move on to extension of this result, which is exactly, I think this is a question that I was asked here about new points. So what I just described doesn't formally solve the similarity search problem, right? Because I assumed that to get this better compression rate, I know all of my points in advance. And this doesn't happen in similarity search, right? I'm going to get a new query point that I didn't know while I was computing the sketch or the compressed representation, and I'm still going to have to estimate this to it. So how can I do it? How can I depend on data that I haven't seen yet? So the answer is, of course, that I cannot. So let me draw the picture here. This is the result I already mentioned. If I know all of the points in advance, I can do this log and this per point. This is tight. If I don't know the points, I can use data oblivious compression. And here, the compression bound is degraded. It's log squared n bits, but it can handle any number of query points that you throw at it. And furthermore, this is tight in the regime where the number of queries, Q, is bigger than the number of data points n. So in other words, if the portion of the data that you don't know exceeds the portion of the data that you do know, then you probably cannot do anything better than data oblivious compression. Data dependence is not going to help you. But still, this leaves open this entire gap in the middle of what happens if you have some queries, you have some portion of the data you don't know, but less than the portion of the data that you do know. And in this case, we can extend our results to get a better compression rate of log n times log q, where n is the number of data points that I do know, and q is the number of query points that I don't know. This is tight in this regime where the number of queries is small and the number of data points, and this is the full picture. You can get something out of data dependence, even if you don't know all of your data, as long as the portion that you don't know does not exceed the portion that you don't know. This is the full picture for distance estimation. And one more result that I want to put on this slide is that I started by wanting to solve the similarity search problem. I solved the distance estimation, and this is natural because if I estimated all the distances, I can pick out the smallest ones and get the nearest neighbors. But maybe I don't have to go to distance estimation. It is in principle possible that just solving similarity search is easier than estimating the distances. And for this problem, this also turns out to be correct. So if you only want the identities of your nearest points and not the distances of those points, then you can get a better compression rate of only log n plus log q bits per point. This is better than oblivious compression, even in the regime where the unknown portion of the data exceeds the known portion. And this is the smallest known data structure for approximate nearest neighbor search in high-dimensional Euclidean spaces. Yes.
Notice that the points come from a distribution. That simplifies it. If you know that points come from some IID from some distribution.
So it depends on the distribution. There are definitely distributions where we know to do this better. For example, if they are uniform, the sphere with the perturbations to get for near term, then we have better solutions. But this depends on the distribution. So I cannot say something in general. Okay. Yeah, but this result don't assume any kind.
Can I also ask? So yeah. For Q, which is linear and not necessarily at least, and so you're writing that the log squared is tight?
Q, which is linear in n, so if Q is linear in n, then you can still get this upper bound because the dependence is logarithmic here. So this still works, right? But you sort of get the same bounds for these two things.
Yeah, I'm just asking the fact that you wrote on the right that it is tight for Q at least n and not at least n.
Oh,
let's say if Q is n over 100.
So if Q is n over 100, I'm pretty sure that I can extend the proof to give a Kernel matrices regime, but I don't think this has been checked. So this definitely this lower bound needs Q to be smaller by n by a constant factor. I don't remember what is the constant factor. So 100 is probably fine. If you tell me like n versus a half n, then maybe you need to massage the proof a little bit. But I think it is going to work. This is not the essential to it. Okay. Okay, next. Okay, so this is the picture for quantifying the defense for making this also solve similarity search. And maybe the last thing I want to say here is that move on to the experimental part. This was just the theory part. So this is a bit trickier than maybe it seems. So let me draw this imaginary axis of bits per point. I started with the oblivious algorithm, and this is definitely also a practical algorithm. And I moved on to the optimal algorithm. But this algorithm, even though it gets the best asymptotic bound, there are some parts of it that don't translate well to implementation. And I can say exactly what. It's not difficult to pinpoint. But generally, it often happens when you try to optimize the best asymptotic bounds, you need to do some things that don't necessarily translate well to implementation. So we also presented a simplified version of this algorithm where all the components do translate well to implementation. This does degrade the compression rate by log n. Still, it is a worst case bound. Still, it's asymptotically better than oblivious compression. This is the result that we get by implementing it. So these are two standard benchmark datasets for images. Y-axis is accuracy, and x-axis is the number of bits that you need to get this accuracy. So higher is better. The comparison here is our algorithm is in red to product quantization in green. So product quantization is the most successful and widely used probably algorithm in practice. Also the prototypical one from the applied literature in computer vision mainly. So as you can see, we are mostly comparable to product quantization. We do a bit worse in the low accuracy regime, a bit better in the high accuracy regime, but overall things are comparable. One more remark maybe to make here is that product quantization, it is really a good algorithm. There's a reason it's been around for more than 10 years and it's very often used in practice. It's also the one, by the way, implemented in the Facebook library that I mentioned earlier. But still, despite all that, it is in the end a heuristic algorithm. It doesn't have those type of asymptotic guarantees that I listed above for our algorithms and for the oblivious baseline. And this means that there is a data set which is going to break product quantization. And we went ahead and constructed it, and this is not difficult. All you need to do is put your points on a line. So it's a one-dimensional data set, but this line is hidden in a high-dimensional space. So this is why we call it diagonal. And as you can see, the result is that the product quantization is struggling a bit. The baseline is not doing anything, and our algorithm works pretty much as well as on the other data sets. So this is maybe an attestation to the merit or potential merit of worst-case guarantees. Okay. So this is everything I wanted to say about the compression part. I would move on to the partition part unless there's any more questions. Okay.
Tal, I have a short question.
Yeah.
If you can go back one slide. So you mentioned that you built this data set that basically has a one-dimensional manifold where the data is lying on, right?
Yeah.
What happens if you have let's say a k-dimensional manifold, but k is, let's say, I don't know, square root of n or a square root of d or something like that?
So basically, where product quantization tends to fail. So product quantization is based on k-means. Where it tends to fail is that the way the points are laid out do not take advantage of the dimensionality of the space. So the lower dimension, the better, because a centroid is always going to, it's a multidimensional. The cluster is a multidimensional object, and if I only use one dimension, then I'm wasting a lot of space there. So the smaller k is, worse product quantization is going to be at hand.
Gotcha, thanks.
למרות שנגיד בדוגמה הזאת, אלגוריתמים הכי טריוויאליים להורדת מימד היו בתור pre-processing, היו פותרים את זה.
נכון, בדיוק, וזה בדיוק העניין ב-data dependence, שאמרתי שלכל data set יש structure משלו, כל data set בפני עצמו יכול להיות קל, אבל אלגוריתם שתופס את כולם ביחד צריך איכשהו לקחת בחשבון בעובדה שהמבנים הקלים האלה יכולים להיות שונים.
אתה יכול להגיד משהו, נגיד דיברת קודם על הדאטאבייס הזה של פייסבוק, מה מספר הביטים שהוא סביר בדאטאבייס הזה או בדאטאבייס אחר? כלומר, האם זה ברג'ים שבו ה-QP עדיין יותר טוב מכם או ש...
לא, אז הם מטבע הדברים הם עובדים ברג'ים היותר קטן, שמעט מאוד ביטים, כן, וזה בדיוק, זה הסיבה, זה הבעיה הידועה של האלגוריתם הזה, הוא ידוע בעובדה שהוא לא משיג accuracy טוב, הוא scales up very well, but then he saturates the accuracy, and there's a different set of techniques for near research if you want high accuracy, but it's called graph-based search, and they have the opposite problem. They're very accurate, but they don't scale. So basically, getting the best of both worlds is like the holy grail. Okay, so let me move on to the partitioning part. As a reminder, the goal here is to quickly identify the most promising pieces of the data sets that we want to search for similar points. And this is usually done by locality-sensitive hashing. LSH is a very simple notion. All it is a partitioning of the space R to the D, such that near points are likely to be in the same part, and far points are likely to be in different parts. This is it. This is why it's called locality-sensitive. The reason it's called hashing is because we also require a fast mechanism to take a point and to quickly map it to the part of the partition that contains it. So if I get my query point, I can quickly map it to the part that contains it and look for similar points only in that part. This is why it's useful for similarity search. Now, classical LSH was a major breakthrough in high-dimensional similarity search. This was a data oblivious algorithm. More recently, but still before my time, it was shown that here too data dependence helps. So data-dependent LSH is asymptotically better than data oblivious LSH. Excuse me? Okay, I think it was corrected. And the question is, what can you do next? And the answer is, again, as I looked in the beginning, maybe we can use machine learning to do this even better. So why would machine learning even be relevant here? Why do we think it could possibly help? So the intuition is the following. The problem we are trying to solve here is to take our finite data set of points and use it to construct a partition of the entire space, which is what LSH is. And this is exactly, and this is the point, this is exactly a generalization problem of the type that machine learning tends to be very good at solving, taking a finite data set and using it to say something meaningful about the entire space. So this is what we want to do. So let me be a bit more detailed. So what is the pre-generalized problem, the combinatorial problem? Before I think about generalization, I can phrase it as follows. I build the k nearest neighbor graph on my data set. So each point is connected to some of its nearest points, to k of its nearest points. And I want to partition this graph in a way that breaks as few edges as possible. Why? Because every edge that I break is a point which is not going to be in the same part as it's one of its nearest neighbors. So this is the problem before generalization, very simple formulation. And the problem after generalization is to have a partition not of the graph, not a combinatorial partition of the finite graph, but a geometric partition of the entire space. Now, we know that there is a formal connection between these two types of partitions. So this is a result from spectral graph theory. It's a very fundamental result. It's a consequence of Chigurh's inequality. It tells us that there is a formal connection between combinatorial partitions of the K-NN graph of a metric space to geometric partitions of all of R to the D that also have a very natural geometric forms, namely they are given by hyperplanes. So we know that this correspondence is there. There is this connection, and we are going to try to realize it using generalization by neural networks. So the method works as follows. We start with the data set, we build the k nearest neighbor graph, and we partition it using usual graph partitioning algorithms. And then the crucial step is to train a network to predict the assignment of each point to the part of the partition that contains it. And this trained network now is my LSH function. This implicitly extends the partition from only the graph to all of R to the D. So if I have a new query point, I can run it through the network. This is my hash function via inference to map it to the part of the partition where the network thinks it belongs. And then I'm going to look for similar points only in that part. So this is the method, and this again are the experiments. These two standard matching data sets. Again, y-axis is accuracy, x-axis is the number of points you need to search to get this accuracy. And our method is in red. It does better and sometimes by a large margin by the previous test. Yes.
You mentioned semantic hashing. It also seems like a baseline.
Which one?
Semantic hashing.
Semantic hashing, right. It is also, it belongs to that family. I think we probably have it in the paper, even though I don't exactly remember, but this iterative quantization and k-means or catalyst k-means, these are like two representatives of this literature. So this literature has either a Euclidean estimator or L1 estimator. So this is the Euclidean estimator, this is the L1 estimator. So I think it should cover it. Yes.
Somewhat understandable. Okay. So you train this network on which data?
So, okay. So I train this network. The data is, this is a data point. Every point in the graph is a data point, and the label of the point, by label I mean the part of the partition it belongs to, yellow, blue, pink, whatever. This is the label. The network learns to predict that.
Train it with respect to the relevant data. So it's not an arbitrary hash function. You tailor the hash function for the type of data you type relevant.
Exactly,
right?
exactly.
The big advantage of a standard pairwise or whatever hash function is that generic.
Exactly, exactly. So those would be oblivious hash functions, and this is a data-dependent hash function, and not just data-dependent, but one which is learned from the data using, a neural network.
So maybe we have like data structure now using similar hash functions that are tailored for data.
There are. It's not just possible, but they actually exist, and this is something I personally work on. I have worked on that and other people, yes.
Why do you need the neural net only to generalize the new points?
Yes, exactly. Without the neural net, what would I do with the new point? Where would I put it?
If you just wanted to index this.
Yeah, I can just use a usual reference.
So this question makes sure that I understand. Like, define the sparse balance cut. This is sort of an algorithm. Okay, the real input is just a set of points, right? All the red arrows. Let's say human.
Yeah, this is the algorithm.
Right? So different algorithm for sparse balance cut might give also different results.
Yes, So this is a meta algorithm. You can replace the partition algorithm. You can also replace.
But mainly the labeling of the sparse balance cut do not count. There's no ground truth there.
Yeah, no. It's an algorithm output, definitely. Yeah. Okay. So any other questions about this?
But for new points, you do assume it's from like the same distribution, right?
So I don't assume it's from the same distribution in an explicit way. I assume that the data set has something in it that can be learned, has some structure, and I just let the network pick up the structure. If the points are, for example, uniform random, and there's no structure at all, then yes, the network is not going to learn anything meaningful, right? But it tries to learn whatever there is there, or this is the hope of this. Okay.
אם אפשר רק לשאול שאלה, יכול להיות שישי כבר שאלת את זה ולא שמעתי. Find sparse balance cut, אין אלגוריתם תיאורטי שעושה את זה, אתה מניח שזה יוריסטיקה.
כן, זה יוריסטיקה. זה אלגוריתם קירוב, אז אנחנו ספציפית משתמשים בקהיפ, שזה local partitioning, אבל זה כמו שאני חושב שגם ישי הזכר, זה מטה אלגוריתם, אז פה אפשר להכניס כל האלגוריתם, וגם פה אפשר להחליף את הרשת, יש לנו חלק במאמר שעשיתי עם linear separators, אז שני הדברים האלה אפשר להחליף, ספציפית אנחנו השתמשנו ב-local partition. כי זה מה שככל הידוע לנו, לפחות בזמן כתיבת המאמר, היה הפתרון הכי טוב פרקטי. Okay. So this is everything I wanted to say about similarity search. So just to quickly recap, and then using data dependence approach to metric compression, we can get the optimal compression rate for Euclidean metrics. They're also for other families of metric spaces that I didn't get to mention, but they're also important. Using this quantified approach to data dependence, we can get fast algorithms for similarity search, and data dependence is necessary to get all these results. And for the partitioning part, we can use neural networks to get better partitions for nearest neighbor search. So I think I'm not. So how much time do I have? About 5 minutes. So I should. Okay, so let me try to move quickly through this linear algebra part. It's shorter anyway. So here the topic is matrix computations, right? We all know they are very prevalent in computing and they are very computationally heavy. And there's a lot of scalability efforts to make them, to scale them up on hardware, software. Let me not get into the details. I'm interested in the algorithmic axis of these efforts. And here the natural barrier is to just reading the content of an n by n matrix is already a scalability bottleneck. So again, let's try to use data and machine learning to alleviate it. So the problem I wanted to concentrate on is the low rank approximation problem, where the input is some matrix and some target low rank, and the output is two skinny matrices whose product should be approximately equal to the input matrix. So this problem has actually an optimal solution in real time, the SVT, the singular value decomposition, but the time doesn't scale, so the degree of the polynomial is too large. And there's a very successful line of work on approximate version of SVD, which get almost the same error as SVD. So this A minus AR is the SVD solution. This is optimal. Every algorithm has to tolerate it, plus some small additional error. And they run in time which is nearly linear in the size of the matrix, so n squared for dense matrices. And how can we get faster algorithms? How can we cross this barrier of linear time? So one option is to rely on the fact that sometimes our matrices don't come out of nowhere. They come from data and they have additional structure that we can exploit. So I'm going to mention distance and kernel matrices. And another possibility is to use the fact that we often don't solve a problem just once. We solve it over and over on different unrelated inputs. And here I'm going to at least mention, or maybe not show you, how we can use test matrices to improve the way we do things on future matrices, and also to prove bounds on how many matrices we need to see. So for all these techniques, we can use the very developed literature on fast linear algebra and speed it up even further with this type of metric quantization techniques that I spent the first part of the talk on speaking about. Okay, so data matrices, what they are is very simple. We have, as usual, some metric space and a way to measure similarity between points. The associated data matrix simply encodes the parallel similarities. So entry ij describes the similarity between point I and point j, where the rows correspond to points and the columns correspond to points. And what are those similarities? They can just be the distances. In machine learning, it's a bit more common to use kernels, which are functions of distances, like e to the minus distance. And one example application is large language models that I'm sure you've heard of, Transformer, BERT, GPT, and so on. So basically, these monstrous deep learning architectures that completely transform natural language processing in the last few years, all they are, or a lot of what they are, is repeated operation, repetitions of an operation called attention, which is really nothing but the matrix vector multiplication of a similarity matrix between two sets of high-dimensional points with a vector. So this is the application. Let me go over our results here. So for distance matrices, we can get an algorithm that gets essentially the same approximation as SVD plus some small additional error. And its running time is nearly linear in n instead of n squared. And this is also tight in a sense. Let me not get into that. And this is the performance of the algorithm in practice. So a blue SVD is the optimal algorithm, the exact one. Approximate SVD is the nearly linear time algorithm for arbitrary matrices. Red is previous work on the same type of matrices. So on the bottom, you can see the error. All the algorithms have pretty much the same error. SVD is a bit better, not by much, because it's optimal. But in terms of running time, then we improve by up to orders of magnitude over the algorithms that don't take into account the fact that your matrix is data matrix. And for kernel matrices, the picture is a bit different here. So here, let me focus on the R equals 1 case. Here, the improvement, there is a subtlety about why this is different than the previous one. Let me not get into that either. Just mention that the more natural way to phrase this result is in terms of approximating the top eigenpair of the matrix. So top eigenvalue and eigenvector. And the running time of this algorithm is n to the 1.5, which is again much faster than n squared. You can push this down closer to n if you really want to, optimize your asymptotic bound. This makes the algorithm very not practical, at least the way we know how to do it today. This n to the 1.5 algorithm is practical, and again, here are the results. So exact computation. This is a baseline based on uniform random sampling. I'm going to maybe say what it is if I have time, and the red is ours, and it gets a much better trade-off between the running time and the accuracy.
אז המקרה של הקרן הוא יותר קשה מאשר המרחקים עצמם?
זה תלוי מה אתה רוצה לעשות. אז את התוצאה מהשקף הקודם, ההבדל הוא בגדול שהשגיאה היא פרופורציונלית לא למסה של כל המטריצה, אלא רק למסה של הכיוון הראשי. אז זה יותר קשה. אם הייתי מסכים שתהיה פה המסה של כל המטריצה, זה לא היה יותר קשה. או לפחות כאילו זה כן יותר קשה בתור בעיה לפתור, אבל זה לא יותר קשה מבחינת החסם מעשית. כמה זמן אתה צריך כדי לעשות את זה. Okay, so now let me maybe quickly, I have a couple more minutes. I can just run through to show you why did I say that this is related to the previous part of the talk, why this is related to metric compression. So this is the usual setting. points in R to the D, similarity that we call kernel, and the associated kernel matrix. And the crucial point here is that multiplying this matrix by a vector is equivalent, and it's very easy, to a weighted form of kernel density estimation, which is a known problem. Let me just write out what it is. So if I take some vector W and I multiply my matrix by this vector, then I write out what I get. It's just the weighted sum of similarities between a fixed point xi to all of the other points xj in the data set. Now, once I want to approximate this type of sums, a sum of things, then it's natural to try to subsample them. I can do uniformly random sampling. This works well. This was the green algorithm from the previous slide. It was better than exact computation in the trade-off between accuracy and error, but you can do better. Chargaff and Similarity, this is something that was kind of known as folklore before, but they formalized it for kernel density estimation. They showed you can use it formally to get a better approximation for KDE. And the idea is very simple. You impose an LSH partition on your data set, and then instead of sampling a uniformly random point, you're going to sample a point only from the part of the partition where the fixed point xi is. And because LSH has the property that near points are likely to be there, then you are sampling the more similar points with high probability. And you get important sampling, so better trade-off between the error and the number of samples. To get this algorithm, we built on it in a couple of ways. And the bottom line is that the overview
is not opposite what you like to do, because the most similar point of those that are not going to fit.
So here, so this is a bit confusing. So kernels larger, like closer is larger as opposed to distance. Where so because it's e to the minus distance.
Yeah, okay.
So it goes in the right direction. And this is the overview of the algorithm is that using LSH you can get an approximation of the KDE, which are the similarities, which is equivalent as written here to approximate matrix of multiplication. And then if you iterate it, you get some version of the power method that you can analyze to get this result. So this is the overview. These arbitrary matrices I'm not going to get into. This is the part where you can use the best matrices to do it. This also turns out to boil down to compressing Euclidean matrix, or in this case, even products. Basically, the approximate SFD algorithm, the one that is nearly linear time for arbitrary matrices, all it is this reduction between metric compression to fast low linear algebra, plug in quantized Johnson integrals, the theorem from the beginning of the talk. This is how the algorithm works. It's not easy. I mean, I make it sound easy, right? But each one of the steps is difficult, but this is what it is. We do it in a knowledge way. I'm not going to go into details. And we get a lot of practical improvements over previous algorithms that use this framework. And we also, in an upcoming work, which is going to be out hopefully very soon, we can also get fact learning bounds on the generalization of this approach. So how many matrices we need to see to get improvement for our algorithm and also for all the other ones that use this approach. By now, there's many of them. And the reason this kind of came out naturally is because our algorithm, the reason it is much faster is because we need a lot less training matrices to get improvement. So this naturally raises the question of how many you need, which is what we sort of answered here. Okay. So this is, I think, everything I want to say for the technical part of the talk. Let me just quickly summarize the whole talk. So again, this is the view of my work on this. These are the papers that I sort of covered. Underlying techniques are the same set of techniques. More generally, the frontier here is to use data and machine learning for better algorithm design, with the principle that every data set potentially has some structure that you can exploit, and that machine learning can potentially help you uncover the structure. Some directions for future work are first standardizing this approach to data-driven algorithms. So we want to design algorithms in a way that seamlessly makes use of data that you have access to and still remains operational on data that you don't have access to, like this quantified approach that I had from Newsman research. And also another concern is, I think it also came up here in some forms, what happens if your base data doesn't have anything to do with the data that you're going to see? So you want good data to help, but you don't want bad data to hurt you too much. And this is also possible to put these safeguards. This is something that maybe it's not clear, but it is something that you can usually do here. And some forward paths here are to first study the principles of designing algorithms in this framework. We talked about it a bit, and also to look at the deployment, case studies of deployment. So some fields, especially medical imaging, this is a front runner. They already use this, and it's interesting to see the kind of challenges they run into. And the other one is maybe a bit more indirectly comes out of what I said, but still does, is scalability in neural network architectures of the algorithmic components of the network. So neural networks are very computationally heavy, basically because they do very repeated computations on matrices and vectors in high dimensions and tensors. So it just seems very tempting to use this set of scalable techniques for high dimensional points and fast linear algebra to speed up neural networks. And this is something that we are working on. For example, this example of language models applying ideas from LSH and the kernel matrices, that's the algorithm that I talked about, to large language models. And the challenges here are basically to balance this algorithmic approach that we have with the reason deep learning actually is feasible and works, which has a lot to do with the architecture parallelism, specialized hardware, and so on. So I think this is it. So thank you.
So fastest we do הזכרת בהקשר של טרנספורמר, איך היית משתמש בזה סתם בעצם?
אז טרנספורמר, אני לא אחזור ספציפי, אבל זה בעצם מטריסת קרנל, אבל הקרנל הוא קרנל אחר, הקרנל הוא to the inner product.
לא, אבל גם תגיד שהייתי יכול לעשות SVD מהיר על המטריצה הזאת, איך היית משתמש בזה בפועל?
אם הייתי יכול לעשות מהיר על המטריצה הזאת, אז את הצעד שבו אני מחשב את ה-attention, שבו אני כופל את המטריצה בווקטור, הייתי יכול לעשות בזמן שהוא רק n כפול ה-low rank.
אבל אתה צריך לחשב גם את ה-SVD, זה כולל הקוסט של לחשב את ה-SVD.
נכון, וזו בדיוק הסיבה, אז כל שדיברתי על approximation זה SVD שהזמן מטריצה של SVD עצמו יותר מהר, בגלל שהוא הולך להיות חלק מהאלגוריתם עצמו, אוקיי. זה לא פריפרוסינג שאני מניח שיש לי בחינם. אחרת פשוט הייתי עושה את SVD. על הטרנספורמרים? בתהליכים.
מדובר פה אחרי שמאומנת והכל ואז...
זה תקף גם לטריינינג וגם לאינפרנס, לטריינינג זה נכון שיש אתגרים משלוש שאין לאינפרנס, הקרדינים צריכים לדור אחורה, זה קצת יותר מסובך שם, אבל בעיקרון אין סיבה שזה לא יהיה תקף גם לטריינינג.
בעצם אתה צריך להיות מסוגל להריץ את ה-GPU בזמן שהוא קומפטטיב עם ההפעלה הזאת.
כן, וזה החלק הקשה.
טוב. בחלק עם ה-Q שאילתות, אתה צריך לדעת את Q מראש כדי לתכנן את המגוון נתונים, ואז כשעברת את Q, שזה הולך ונהיה יקר, מה קורה?
אז אתה צריך לדעת את, לפחות מבחינת הצורה של האלגוריתם התיאורטי עובד, אז צריך לדעת מספר ה-queries כדי לבחור את ה-compression. אני מקבל מספר ה-queries, ואז לפי זה אני יודע כמה ביטים אני צריך כדי להתמודד עם Q-queries.
אז אם המספר בפועל היה יותר גדול, פשוט זה יענה לשאילתות, אבל בזמן שהוא יותר גרוע מהחסם שאפשר לדעת אם הייתי יודע.
במקום שיותר גרוע, כן.
אוקיי, תודה רבה.
לא, יש לך באמת, יש לי את ה-F זה כאילו...